Okay, so now I want to do question 10. So we have a linear transformation, and we have a basis v1, v2, v3. It doesn't really matter what the basis is, just as long as we know that v1, v2, and v3 are a basis for this problem. Okay, and we know that t applied to v1 is equal to v1 plus v2. We know that t applied to v2 is equal to v1 plus v3. And we know that t applied to v3 is equal to v2 plus v3. So we know the matrix relative to the basis b. Well, the first column is going to be t applied to v1 relative to b, relative to the b basis. The coordinates of t applied to v1 relative to the b basis. Well, t applied to v1 is v1 plus v2, so this is going to be 1, 1, 0. Again, because this is 1, 1, 0. And the second column, sorry, this work is all disorganized. I don't know why I'm doing it like this. The second column is going to be t applied to v2, the coordinates of those in the b basis. Well, tv2 is v1 plus v3, so this is 1, 0, 1. So the next column is 1, 0, 1. And then the last column is going to be t applied to v3, and again, that's going to be relative to the b basis. T applied to v3 is v2 plus v3. So the coordinates of v2 plus v3 relative to the b basis are 0, 1, 1. So this is going to be 0, 1, 1. Okay, and it looks like the correct answer choice then is answer choice B. That would be the correct answer choice. Okay, now to figure out the transformation relative to the E basis, let's think through this. So we need to find, so what we want to find is t applied to some vector. So actually, let me use different colors because I'm now on problem number 11. This is the work for problem 11, but I don't have a lot of room, so I'm going to do it up here. So we want to find the matrix M that satisfies the following equation. So t applied to the vector v relative, so I guess I should say the coordinates of t applied to the vector v is equal to m times this vector, times the coordinates of v relative to e. Okay, we want to find this matrix M. Okay, so how can we do this? Well, all we have is the matrix M sub B so far. So the equation that we know so far is that TV applied, the coordinates of TV in the B basis is equal to MB times V, the coordinates of V, in the B basis. Okay, but we want to compute it with, we'll start by looking at the right-hand side. We want to be able to put in the E coordinates, the E coordinates of the vector. Okay, so what we need to do then is have the change of basis matrix here that takes us from E coordinates to B coordinates, and now we'll multiply it by V times E, the E coordinates of V. Okay, because what's going to happen, this matrix times the E coordinates for V are going to give us the B coordinates. And that's what we know how to compute, okay? So let me just write, what the previous problem tells us is that the B coordinates of TV are equal to this matrix MB times the B coordinates of V. Okay, so if we want that to be the E coordinates, then we have to multiply by this change of basis matrix that takes us from the E coordinates to B coordinates. Okay, and now if we want the E coordinates here, well, remember the change of basis matrix from B coordinates to E coordinates times the B coordinates of TV. This is going to give us the E coordinates of E, or the E coordinates of E. So really the equation that we have then is TV, the E coordinates of TV are equal to the change of basis matrix from B to E times the matrix that we found in problem 10 times the change of basis matrix from E to B. And so now we need to figure out what each one of these things are. Okay, now the change of basis matrix from B coordinates to E coordinates, this is just the matrix whose columns are going to be the E coordinates of V1, V2, and V3. Okay, and so what is that? Well, that's just going to be the columns of the V1, V2, and V3. And for this, we need to look at the previous problem. So V1 is 1, 0, 1. This is 1, 0, 1. V coordinates, and then let's see, V2 is 0, 1, 1. V2 is 0, 1, 1. And then V3 is 1, 1, 1, I'm pretty sure, but let me double check. Yeah, V3 is 1, 1, 1. Okay, that is the change of coordinates matrix going from B coordinates to E coordinates. Okay, and so now the change of coordinates matrix going from E coordinates to B coordinates is going to be the inverse of this matrix. So we're going to row reduce. Actually, let me make sure we haven't already done this up at the previous problem. Okay, I think we actually did that up in the previous problem. Yeah. So we got that the inverse. We got that the inverse is this red matrix here. That's the inverse. So we can actually use this down below. So let me just use the work that we've already done. So I'm going to erase some stuff down here. Come on. Okay. So now the coordinates going from E to B, what is this? Okay, so 0, minus 1, 1. 0, minus 1, 1. Then the next column is minus 1, 0, 1. And then the, whoops, what the heck? And the last column is 1, 1, minus 1. Okay, so then we're going to do this, this matrix times the MB matrix times this matrix here. Okay, so first I'm going to do 1, 1, 0, 1, 0, 1, 0, 1, 1 times 0, minus 1, 1, minus 1, 0, 1, 1, 1, minus 1. Okay, and what I get is 0, okay, this is minus 1, this is 1, this is 0, this is minus 1, this is 0, this is 1, this is 2, this is 0, this is 0, and now I'm going to multiply that by the change of basis matrix from B coordinates to E coordinates. So that's going to be 1, 0, 1, 0, 1, 1, 1, 1, 1 times minus 1, 1, 0, minus 1, 0, 1, 2, 0, 0. Okay, what does that give me? Minus 1. That's minus 1. Then the next row is going to be 1. And then the next one is going to be 0. Okay, then it's going to be minus 1. It's going to be minus 1 plus 1, which is 0. Then it's going to be 1. Then it's going to be 0. Then that's going to be a 2. Then that's going to be a 0. And that's going to be a 2. Okay. So now so this right here is the final answer. And so let's double check our answer. Okay, so what do we know? So we know that T applied to V1 is equal to V1 plus V2. And we know that in standard coordinates, v1 is 1, 0, 1. So let's do a little scratch work here. So let me do scratch work in red so it stands apart. So this is -1, 1, 0, 0, 1, 0, 2, 0, 2. Now I'm going to multiply this by v1 written in e coordinates, which is 1, 0, 1. And what this gives me is 1, 1, 2. And according to the formula, that should be equal to v1 plus v2. So let's see what v1 plus v2 is. So if I look at v1 plus v2, I should get 1, 1, 2, which is exactly what I get. Okay, so it satisfies the right equation for TV1. Let's see if it satisfies the right equation for TV2. So when I put TV2 here, or when I put V2 there, written relative to the E coordinates, so what is V2 again? V2 is 0, 1, 1. So when I multiply this by 0, 1, 1, what I get is 2, 1, 2. And according to the formula, that should be equal to V1 plus V3. So 2, 1, 2 should be the E coordinates for V1 plus V3. So let's look at V1 plus V3. V1 plus V3 is 2, 1, 2, which is what we got there. And then finally, let's check it to make sure that it also works when we multiply it by V3. So the V3, the V1 coordinate, or the E coordinates for V3 are 1, 1, 1. So when I multiply this by 1, 1, 1, what I get here in the top entry is going to be 1. In the next entry, it's 2. And in the bottom entry, it's also 2. And according to the formula, that should be V2 plus V3. So let's do V2 plus V3. If I do V2 plus V3, that's 1, 2, 2. Which is what I got there. Okay, so that verifies, since I verified the formula on a basis, that tells me that this formula is the correct one. Okay, and so the problem is going to be that there's actually not a correct answer here. So again, this is a typo. So the 1 and the 1 and the 0 in that middle column should be switched. So that should be a 0, and that should be a 1. Okay. So that's it for the video for today, and that is actually the end of the first practice test.